All right, folks, I want to talk about a few more binary relations on numbers. I've got 3 of them right here on the screen. Let's look at them in turn. Each of these are going to relate to numbers, and each relation has a name that's kind of suggestive of what it is the relation is meant to convey. So the first one we'll look at is called square of, and it relates numbers to their squares. Now this is a funny relation. It could be a function, right? But we've chosen to write it as a relation. So now we would have a proposition, square of, and we would say, okay, square of 1, 1, square of 0, 0, square of 2, 4, square of 3, 9, and so on. Not a particularly useful relation, but something to see. Next up, next nat. This is a relation that says, okay, I'm going to relate each number to its successor, right? So it'll say next nat 0, 1, next nat 1, 2, next nat 3, 4, next nat 46, 47. All of that lines up. Okay, lastly, next EV. So next EV says, well, I'm going to relate a number to the next even number. There's 2 ways of doing it. Well, the first way is, well, if I have a number n and the successor of n is even, then that's the next even one, just the successor. If I have a number n and the successor of that is even, well, okay, then the successor of our number is even. We could have equivalently said this. If I have a number n and n is even, then s of n. So let's take a second to look at this one. What are the next even things? So for, say, 0, what is 0 related to in next even? It should be 2. Which constructor will do it? It'll have to be this one. Because just successor of 0 is 1 will not be able to prove EV1, so it'll be the NE2 constructor. Okay, what about 1? Which constructor will we use? Well, we'll use NE1. Why? Well, we'll have a number n, 1. We'll have a proof that successor of n is even, EV2, not hard to find. And then we'll find that n, s of n, right, are related in XDV, so that 1 is related to 2. Again, maybe not the most interesting relation, right? This again could also be defined as a function, but something to see. Let's do one last one. I want a relation that relates numbers to their predecessors. What do we want to write here? So we have a function that more or less does this already. How might you define it? Pause the video, give yourself 5 minutes to do your best job writing it out. Welcome back. So I would define it this way. Prev nat relates a natural number to a natural number. Pn of n is a nat. Says prev nat s of n is n. That's simple. So what would be related here? 5 would be related to 4. 4 would be related to 3. 3 to 2. 2 to 1. 1 to 0. Would 0 be related to anything? No. Right, let's prove it. There is no natural number n such that prev nat 0n. So intros contra. Destruct contra as n h. So we have a number n. We need to show that prev nat 0n. Inversion h. No way. Okay, not a complicated proof, but I want to highlight something here. This is another advantage of inductive propositions. This prev nat, this is the true predecessor proposition, not function, right? The function had to be total. When we defined pred, the function, we found that, okay, well, pred 5 gives the right answer, but pred 0 does not. It says pred 0 is 0. With an inductive proposition, we can write something that's like a function, but is partially defined, not totally defined. There are inputs which nothing is related to, whereas pred, the function, has to be defined for every possible natural input. It's a requirement of Coq. So one reason why people like to do work in the propositional world is it lets them reason about partial functions like this really cleanly, whereas in Coq, every function you write has to be total. If you want to talk about partial things, then you have to work in this slightly different world. Wanted to highlight this as one of the reasons why this propositional thinking is important. Okay, in the next videos, I'm going to talk about a couple more relations. I've got one on lists and two on trees, and then I'll go on to the mystery relation assignment, one of my favorites. Talk to y'all soon.